करूँ start? Hello, sir. Yes, sir. You can start after 5 seconds. Yeah.
The radio frequency range. Now, in radio astronomy, we look at not photons that are typically detected in an optical telescope, which is the most commonly perceived telescope, where there's a camera, there is some optics that focuses the rays onto a focal plane, and then you have something like a CCD which collects photons. Unlike that, in radio astronomy, what we do is we sense waves. So the wavelengths are large enough that we have coherence. So we don't have almost like a whole uh, array of photons, which gives rise to waves. So radio waves are collected using an antenna. And the interesting thing about this is that not only are we able to sense the amplitude of these energy packets that come to us, but because there is a length scale of coherence, we also have a sense of phase. So this is what we call coherent detection. So we have information about amplitude and phase of the wave packets of photons. So we see them as a wave. Now, what is the actual quantity that is coming out from the source we are studying? So that we call as specific intensity, which is independent of the distance of measurement. So this is a quantity that is intrinsic to the source that is emitting the radio wave. And this is the mathematical formula, but you can think of it as the intrinsic brightness property of the source of radiation. So whatever it is, the object that is generating the radio waves, this property is intrinsic to it. But what we actually end up measuring is something called as the flux density. So it is the amount of this power that is actually falling on us, and that is what we end up measuring. So we, from the flux density, we can try to infer the effective brightness of the source. And unlike brightness, flux density is something that goes as 1 over so 1 over distance square from the source. So the farther and farther you go away from a source of radiation, the lesser or the weaker the flux density becomes. And just to give you a sense of context, the kinds of power that we measure in radio is measured in a unit called the Jansky. So one Jansky corresponds to 10 raised to minus 26 watt per meter square per hertz. Okay, so if you just the level of a few Jansky, sometimes we measure things at the level of a millijansky, and we've done very, very deep sensitive surveys of the sky where we are measuring, like microjansky. So that's 10 raised to minus 32 watt per meter square per hertz. That is how sensitive some of these telescopes can be. So when I say a telescope, the first thing you would think about when I say a radio telescope is an antenna, which is the fundamental sensor in radio astronomy. Different types of antennas, and I will not be going into the details, but let's think of an antenna in the most simplest sense, like a parabolic dish. So if you look out onto various TV towers where you have, you have a receiver dish, it's typically a parabolic dish. So your dish TV or Tata Sky, etc., etc. You have a small dish, and that dish, just like in an optical telescope, focuses the radiation to a focus, and at the focus there are some fundamental properties of an antenna, most of them relating to the size and the frequency. So the gain of an antenna is corresponding to its sensitivity, which is how directional the antenna is in terms of the power it receives. And that is proportional to the effective area of the antenna and inversely proportional to the wavelength square. So the another property of the antenna is how small an object you're able to see with it. We call this resolution, and that is something we may be familiar even from, like a microscope. It's how small an object you can see. So for a radio telescope, the resolution, the angular resolution you're able to see is proportional to the wavelength and inversely proportional to the size or the diameter of the dish antenna typically. So these are some properties that determine how faint and small an object you're able to see. There is one other quantity that tells you how clean an image you can make with a radio telescope, which is basically how how do you reduce the noise in your data, right? And this equation is called the radiometer equation, which basically tells you that you have some intrinsic noise in your experiment. This noise comes from both your own electronics in the, say, radio telescope receiver. There's also some noise that gets added from the source you're trying to study. So whether you're looking at a radio galaxy or you're trying to study radio emission from our own galaxy, that also adds to the noise in your total system. You can also have noise contribution from our atmosphere, for example. So all of that goes in the numerator. So you have a noisier input, the total noise in your system is large. But there are techniques you can use to reduce the noise in your experiment, and that is the denominator. You can observe your source or your target over a wider bandwidth. Okay, so a large range of frequencies you can observe, or you can observe your target for a longer duration of time. Okay, this is, I think, intuitive. For example, even with our eyes, if you're able to look at the dark sky and stare at it longer and longer, slowly you start seeing point sources that you couldn't see before because your eyes adjust. But this saturates. There's a limit at which this saturates. So the same logic applies even in radio astronomy, where you can reduce the noise by observing a target for longer duration. Now, all of this is well and good, but what if you want to start building larger and larger radio telescopes? There's a very nice technique that is used fundamentally in radio astronomy to increase the size of your telescope. We can think of one really, really large radio dish. Maybe the size of the dish itself is like 20 meters across. This is possible, but there's only so big you can make a large radio dish. Because once you make the dish larger and larger, first of all, mechanically it is very difficult to make such a dish. Then they'll have other problems of how do you steer the dish? How do you make it look in one direction versus another? So practically, there's a challenge. Here we can use this really nice property I mentioned of sensing waves and not photons per se, where the wave that comes to you from the source has inherently some sense of coherence. Coherence is the correlation between the spatial information that is present in the data that you receive. So the waves that come to you from one direction of the sky can be sensed effectively, not just using one antenna or one dish. You can put many dishes and multiply the data that comes from individual dishes. Okay, so I'll take 2 minutes to spend some time on this topic. So assume that you have a wave front coming from a direction in the sky. That wave front will hit one antenna a little bit faster than it hits another antenna. Okay, so there is some delay. Now you can take the voltages that come at the output of these antennas or your receivers and then correct for that delay in electronics and add them. Or you can take these voltages that come from your antennas in your experiment and multiply them. So what this multiplication process does effectively is the following. And I know this is a kind of complex looking equation. I try to break it down for you. So what you have on the right side is what comes to your radio receiver. So the first term is that intensity or brightness that we discussed in the very first topic. So this is the intensity that comes intrinsically from the source. Then each of your individual antennas has some beam that senses this radiation. The next part, the exponent term, is the trick that converts this into meaningful information for us, where what you're doing is actually a Fourier transform operation. So what you're doing is you're taking the sensing aspect of the individual antennas and the source radiation and taking a Fourier transform of this. And what you have on the left is the output that you actually observe. So the quantity on the left, which is called the visibility, is what any large radio telescope, which we call an interferometer, observes. So by taking this visibility on the left, you can go back and reconstruct the intensity on the right. So you can take an inverse Fourier transform and get that intensity term, which is the actual quantity you're interested in. So this is the heart of radio astronomy interferometry, where the spatial coherence function or visibility and the intrinsic sky brightness have a Fourier transform relationship. With that being said, let's see what happens. Uh, this quantity, the pink curve that you see on top, is the envelope that is set by the primary beam of your antenna. So each individual antenna has a beam, and that is what that pink curve is. But now when you put two antennas and you start multiplying them, you can start sensing more detail than your individual primary beam allows for. So the larger the spacing or more the number of these dishes, the finer you can sample the beam. So effectively your beam width or the spatial scale that you can sense with more than one antenna increases. So more the number of these antennas and further apart they are spaced, the finer the scales you can sense. So effectively what you're able to do with this trick by putting many small dishes far apart is you can treat all these antennas together collectively as one huge radio telescope. In fact, what you can do is you can put these antennas at certain distances and let the earth rotate. Okay, when the earth rotates, your source that you're observing projects different length scales across your two antennas that you have or many antennas that you have. And you can use your entire earth as a partner in creating a much larger radio telescope than your few individual telescopes. So this is called synthesis imaging or rotation synthesis. And effectively what you're doing in this case is whatever data you're able to sample in your visibility or your UV plane, you're able to fill that plane more densely just by the trick of the earth rotating anyway. So one beautiful and one of the biggest radio telescopes we have in the world today is in our very own country. So this is called the Giant Meter Wave Radio Telescope. It is located close to Pune in India, and you have 30 dishes with almost 27 kilometers apart. Okay, and each of these dishes is quite large. And this creates a huge radio telescope operating at a wavelength of a few meter scale. And this is among the most powerful radio telescopes in the world today. And you can do all kinds of interesting science that I will come to quickly. So let's look at the science behind the radio emission. Okay. So broadly, there are three different types of things you can study or three different types of radiative processes you can study in radio astronomy. There are non-thermal processes, thermal and spectral light processes. So very quickly, one by one, I'll come to each of these. So let's start with the kinds of objects that are bright in radio. Okay. So you have a whole array of objects that you can study using only radio astronomy. So first of all, one of the coolest objects out there are things like neutron stars. So pulsars are very compact neutron stars that are rapidly rotating, and these emit radio waves that you see as pulses. Okay. Another interesting phenomena are you can see the central engine inside huge galaxies. So many galaxies are known to host at their center a supermassive black hole. And these black holes are basically engines that are powering out large jets in both sides that you see on the top right corner. And these are called active galactic nuclei. And these are bright in radio. These are among the largest, most energetic phenomena. And you can study very distant objects using these radio emissions from these AGNs. On the bottom are stellar nurseries, so places where the stars are born. Okay, and these are also very bright in radio, and they create also beautiful nebula-like regions in optical as seen here. But remember, in optical, these kinds of regions where the stars are formed are very dusty. You cannot really see the central part of what is actually going on. That is studied using radio. And on the right bottom, you can study different galaxies. So the pictures there are not made in optical telescopes, even though you can see spirals and so on. These are actually the hydrogen in the galaxies that we're able to image, and we can understand the galaxy properties, how big galaxies are, how fast they rotate, all using radio. So very quickly, so what is synchrotron radiation? Synchrotron radiation is a non-thermal process. It's a very energetic process where you have relativistic electrons, electrons moving almost at the speeds of light, going rapidly around magnetic field lines that are there in galaxies. Our galaxies are the galaxies. So our own galaxy is very, very bright in synchrotron radiation. So when you make an image of our own galaxy and we want to study our galaxy at low frequencies, it could be 100 megahertz, 400 megahertz. The galaxy is very bright. In fact, you can't see other phenomena very well at these frequencies because this dominates all our antennas and receivers. Okay, so synchrotron is a fundamental mechanism that is very bright and creates bright radio emission. So we are able to study our own galaxy and other galaxies in synchrotron, and we are able to also understand the magnetic fields and the magnetic properties of all these sources because of synchrotron radiation, because synchrotron radiation is highly polarized and the polarization depends upon the alignment of these magnetic field lines. So next is Bremsstrahlung, okay, which is basically something that we've also studied in various physics courses. You have an electron. I mean, the electron is moving, and it moves past a heavy nucleon, such as the proton. It changes its direction, okay, and this gives rise to radiation. And this is called thermal Bremsstrahlung. Okay, so this is another process that we study, yeah, and those regions that I mentioned where the stars are born, which are otherwise opaque in optical wavelengths, Bremsstrahlung is very bright in these regions. Okay, and finally we come to line emission, where basically, just as we know in atomic physics, you have electrons when they transition from one energy state to another energy state, either in atoms or in molecules. You have line emission. In molecules, you have more different processes. Molecules can vibrate or rotate, and they again generate lines. Okay, the most abundant element in our universe is hydrogen. Okay, and neutral hydrogen, so hydrogen with the proton and the electron in the ground state in the 1s shell, emits a photon naturally, which has a wavelength of 21 centimeter or a frequency corresponding to 1.4 gigahertz. Okay, what is actually happening here is when you have an electron and a proton that are aligned in the same spin, okay, that is a slightly unfavorable energy state. So with time, the electron will naturally flip its orientation to be anti-aligned to the proton spin. So this is a more energetically favorable state. This spin flip transition emits a photon with this 21 centimeter wavelength or 1.4 gigahertz frequency. So even though this transition probability is very low, just because there is so much hydrogen and neutral hydrogen in the universe, we can use this 21 centimeter of hydrogen to study hydrogen gas in the universe. Okay, this is such an image of our own galaxy. So it's a very different image than what one would think of when you think of the Milky Way. Remember, this is not a top-down view. We are not looking at this spiral arms from the top down, but from the outside. Okay. So the way to think of it is that the central bright line. Is there a question? All right. The central bright part, which is the flat like a white line, is the plane of our galaxy, and that is where all the spiral arms lie. And above and below are above and below the spiral arms. Okay. We're looking at it from the outside. And the bottom, there are two bright patches. Those are two satellite galaxies of our own Milky Way. They're called the Large and Small Magellanic Cloud. So we're able to map out the gas distribution of our galaxy using the hydrogen line. And this was made using two telescopes in US and in Australia. In Germany and Australia. So now we can do cooler things with this 21 centimeter line from hydrogen and study not just our galaxy or nearby galaxies, but you can try to understand the formation of the very first stars and galaxies in our entire universe. This is a big open problem in our understanding of the universe. We don't really know exactly when and how the first stars and galaxies formed. Because in the Big Bang model of cosmology, which is the currently accepted model, when the universe forms, initially there are just protons, electrons. These combine to form atoms, and then we don't really know what happens, and suddenly there are galaxies. Okay, how did the first stars and galaxies form? How did they evolve? What kind of radiation did they emit? All of that is a missing piece of the puzzle, and the only way we can study this process is to use the 21 centimeter or the 1420 megahertz radiation from neutral hydrogen. We can understand how the hydrogen content of the universe evolves as a function of time. And what we call time in cosmology, correspondingly, we use the expression redshift. So, higher the redshift, further back in time we are looking. Okay, so the younger the universe is. So, we think from our various other models that the first stars and galaxies should have formed at a redshift of 15, which corresponds to the age of the universe when it is, I don't know, a few 100 million years old, which is very, very young. For context, right now, we think the universe is about 13.8 billion years old. So, effectively, by trying to study or detect hydrogen from a redshift of 15, you are able to look back at the universe as it was about 13.4 billion years ago. Okay, but it's a very, very, very weak signal because clearly it is coming from far away, and you're going to look at it through all the other noise in your local universe. Okay, so this is the challenging problem. And the kind of signal that you may expect, it looks like this. So, because of this process of redshifting, because you're trying to look for photons that come to you from much, much earlier, what happens is that the original photons or radio waves that were emitted at 1.4 gigahertz get stretched out because the space time of our universe is expanding. What happens is that this wavelength gets stretched out, and today it should reach us at very low frequencies. Okay, so just let me just the process of the expansion of the universe stretches out the wavelength or correspondingly reduces the frequency of the 1.4 gigahertz of hydrogen, and today we should be receiving it at much lower frequency. So based on when that photon was emitted, we could see it anywhere at few megahertz all the way up to 200 megahertz to study the process of the formation of the first stars and atoms in the universe. This period, typically, when the first stars and galaxies form, is called the cosmic dawn. Okay, and preceding the cosmic dawn is a period called Dark Ages, and after the cosmic dawn is reionization. So this entire set of um, period, okay, is something that we can study using the 21 centimeter from hydrogen, and this is a very, very powerful tool. Because the signal is very, very weak, I will emphasize that we have never detected this signal. This is an open problem, and we here at the Raman Research Institute and several astronomers and cosmologists from around the world are actively trying to detect this signal. So, whoever makes the first confident detection will be able to tell us something dramatic about the birth of the first stars and galaxies in the universe. Now, I quickly switch gears here and tell you about why it's nice to do this not just from Earth, but we should be going to space. Okay, so again, I'm showing you the the electromagnetic spectrum. To the right is the radio waves, and to the left are the higher energy things like X-ray and gamma rays. Now, we do receive radio waves on Earth, which is why we have nice telescopes like the GMRT that are able to collect data and do really nice science. But despite this, there is a barrier that stops some radio waves from coming to Earth. Okay. And this is because our atmosphere has an ionosphere, okay? The ionosphere has plasma in it. So basically it has electrons and protons. But electrons, because they are lighter, they are more important for our discussion here. So electrons cut off radio waves that come at low frequencies, okay? So any radio waves that come to enter Earth from space at frequencies lower than 10 megahertz are cut off because of the ionosphere. And this cutoff frequency is proportional to the square root of the number of electrons. So during the day, you can get more radio waves at low frequencies, maybe 8 megahertz, but I mean during the night. But during the day, if it's a very active sun and an ionosphere is very rich, there are a lot of electrons, then this cutoff frequency can increase even up to 30 megahertz. Okay. Because of this, we are not able to study a lot of processes at very low frequencies. And some of the things you necessarily have to go to space are the following. You can study exoplanets and how they interact with their stars at low frequencies. So at below 10 megahertz, we can study exoplanets, we can study our own galaxy's properties, and we can study what I mentioned earlier, the dark ages, the 21 centimeter from dark ages. Okay, so this motivates us to go to space. But let's say we just put a telescope above space, above Earth in space, okay, something orbiting Earth above the ionosphere. There is one big challenge, which is the Earth is actually very radio loud, okay, because for essential reasons like communication, we have satellites going around Earth, we have FM transmitters that transmit radio frequencies. The Earth is very, very noisy. So for astronomy, you want to be observing your data, collecting data in a radio quiet place. So if you go to space, you see a lot of interference from things like FM radio, TV, satellite communications, maritime communications. Okay. So it's not possible to shut down these operations because these are essential operations. What you need instead is a radio quiet location in space. And luckily for us, at least as of now, such a space does exist. Okay, which is the far side of the moon. So you may remember that when you look at the moon, you're always looking at the same face of the moon. There is the back of the moon that we actually never see on Earth because the Earth and moon both rotate at the same 24-hour period. Okay. The far side of the moon is the region that we don't see, but that doesn't mean it doesn't get sunlight. Okay. It is not dark. It also receives sunlight and gets night and day based on the lunar orbit with respect to the sun. But it is always blocking radio waves from the Earth. So if I put a telescope behind the moon and try to observe it and I try to operate the telescope, I'll be able to get good quality data at radio frequencies when because the radio waves from Earth are being blocked. Okay, and this is a very nice location to put a radio telescope. So people can do different kinds of things. They can have a radio telescope orbiting the moon and collecting data whenever it is protected by the moon. Or you can put something like a lander. You can deploy a whole array of telescopes. Like you can put an interferometer, maybe not something like GMRT, but something else. But you can put an interferometer on the moon and you can collect data. Okay. And the reason why this works is because the moon blocks radio waves. Okay. Just like, let's say you're in a building and you don't get good signal because you are at the end of the day concrete and metal structures are blocking the radio waves from coming in, but you move to a better location, right? And then you can hear the radio waves. The moon does just that. The moon blocks radio waves. So when you're behind the moon, radio waves from Earth are blocked, but radio waves from the universe are still coming to you. And when you come back towards the near side, the side of the moon you can receive the radio waves. So with that in mind, our group here at the Raman Institute has proposed an experiment called Pratush, which is the expected if approved, to orbit the moon. And when it is on the far side, it will collect radio waves. And on the near side, it will transmit the data back to Earth. And the primary purpose of Pratyush is to try to detect the 21 centimeter signal from the first stars and galaxies from the cosmic dawn. So very quickly, this is an animation of what Pratyush would look like when it is orbiting the moon. When it is on the far side in the shadow of the Earth and the sun, it will collect data. When it is on the near side of the Earth, facing Earth, it will downlink the data. But just to remind you that we are not the only ones trying to do this. There are many groups across the world who are trying to do this. But there are also other interests in orbiting the moon. There could be a lot of commercial interest to kind of start deploying things on the far side of the moon. So very quickly, we may lose the last radio quiet site accessible to humanity if this is not regulated. So there are bodies from across the world, including astronomers, who are trying to see if the far side of the moon can be protected and kept radio quiet. But only time will tell. So whoever gets to go sooner, they will get better quality data. Now, with that, I come to the summary. I know I've covered a lot of topics, but hopefully you appreciate that we use radio waves from astronomical processes to study the universe. Fundamentally, the sensor is an antenna, but to add more and to make a bigger and bigger antenna, you don't have to construct one big antenna. You can have many small antennas and combine the data and use mathematics to effectively make it a larger telescope using the process of interferometry. There are a lot of processes that emit radio waves, and 21 centimeter emission from neutral hydrogen is one such process. And we can use this not only to study our own galaxy, but also to study the very first stars and galaxies that ever formed uh, to address problems in cosmology. But to study low frequencies, okay, both to understand cosmology as well as our own galaxy, if you want to study this at very low frequencies of few megahertz or 10 megahertz, we cannot do this on Earth because the ionosphere cuts off these frequencies. So you want to go to space and to a radio quiet location in space. One such radio quiet location is the far side of the moon. Okay. And finally, I will leave some references here. The first few links are just some summary slides, different slides covering similar topics that I have today. There are also some textbooks for those who want a lot more detailed information. And there's one popular article on 21 centimeter cosmology at the bottom. So I will stop here, and if there are any questions, I'll take questions. Thank you.
Yes, thank you so much for the talk, Dr. Mayuri. I think it was a really nice journey from how, let's say, we view the universe through the optical lens and how we view the universe through, let's say, radio telescopes, right? So the transition was really nice. Thanks for taking us through this journey. And thanks for walking us through the power of radio astronomy in general. And I think Pratyush is a state-of-the-art instrument. So it's really nice to see that. It's really nice to see the direction we are heading towards. So amazing. So I have one question here.
Mhm.
And I think you have already covered this, but maybe if you could reiterate this point once again. So a person asks, what is the biggest advantage of space-based radio telescope over the ground-based? Maybe if you could reiterate that once again, it would be nice.
Yeah. So there are actually, I covered one, but let me cover a few more advantages. Okay. So first of all, there are some frequencies that are inaccessible from the ground. Okay. So you can do a lot of radio astronomy from the ground, unlike things like X-ray astronomy, where you have to go to space. But even in radio, if you want to do low frequency radio science, you have to go to space. You cannot do this from the Earth. And the three things we can study with this are you can study exoplanets and how they interact with their host stars. You can understand our own galaxy because our own galaxy's emission has a change in the spectrum, as you may see in the central figure, as well as you can study the very, very early universe, even before the first stars and galaxies formed. All of these three processes are observable only at frequencies of few megahertz, which you cannot access from the ground. Okay, so that is one advantage, is you can understand things that you cannot potentially ever detect on the ground. The few other advantages are if you go to the far side of the moon, for example, you have better quality radio data because anywhere you go on Earth, you will have some amount of interference. Even if it is not direct interference from some tower right next to you, if you go to a radio quiet location, you still have indirect emissions such as transmitter in, for example, a radio transmitter in Delhi could be reflecting off an aeroplane that is passing overhead somewhere, and I received that in Ladakh. We have seen that happen in our data. Okay. So you have better quality data because it is more radio quiet in space in the lunar far side. The second is even at the frequencies where we do receive um, data on the ground, okay, ionosphere can do things like refract or reflect or attenuate. Okay, so the ionosphere is like a medium, just like if you're trying to take a optical image through water. Water is transparent. If it is stable and still you can, it's clear for you. But the ionosphere does the same for radio. If you go to space above the ionosphere, your quality of data is better. And the third is it is very, very, for very sensitive experiments, you want to be in free space because when you design an antenna that is very beautiful and precise, but you place that antenna such as on a surface, like on soil or on a rock, your antenna properties change. So these are not problems that are seen by general telescopes, but if you want to build more sensitive telescopes for astronomy, you please. So these are the three main advantages of going to space.
Right. And another interesting question here. So, since we are moving away from ground based to space based radio astronomy, what is the biggest hidden challenge building a telescope that can't be repaired once when it has reached its orbit?
Yeah.
Please, Mayuri. Yeah.
Yeah, I mean, it's a very, very difficult question to answer. I think, especially people here doing anything from space is. Um, you so there have been extreme examples of things that have been repaired in space. The most notable example being the mirror on the Hubble Space Telescope that was repaired by a human being in space. Ideally, we do not want to do those things. So you want to keep your experiment design as simple as possible so that less things can go wrong. You also want to make sure you build in a lot of one thing fails, you have a backup to switch to. And of course, extensive ground testing and modeling of how your data quality will degrade if your telescope performance degrades. So if you have an expectation for that, you can do some amount of post-processing to correct and ensure your experiment life improves. But it is absolutely correct. It's very challenging. So you have to be that much better at the planning, engineering, and analysis.
And also, maybe if you can walk us through the strategy that you have adopted. So, let's say when we are on Earth, right? The detector can be in one particular place. I can have my instruments in the other place. I can do my analysis elsewhere. But when it comes to this, right, your instruments itself generate noise. So, if you can walk us through a couple of strategies that you have adopted to take
Yeah,
care of
so I
this.
mean, first step is extensive ground testing in the lab. So then you learn a lot more about your instrument, you know what tends to fail, you understand your data quality conditions. That is the most important strategy we adopt. The second is a lot of modeling. So not just doing tests in the lab, but also tests in how you do your data analysis. Because finally, at the end of the day, your data quality is only as good as the tools you have to analyze the data. And then to have, for example, we want I'll give you a very quick example. I won't go into details. We have a counterpart experiment that operates on ground. Separate the antenna from the electronics and keep them far away so that the noise from the electronics is not received or picked up by the antenna. We don't want to do this in space because you don't want two moving parts that are far away just to reduce the risk of any failure in deployment. So instead, we put everything together and you have to think of novel techniques to improve your electronics to have lesser noise in your electronics so that your antenna doesn't pick it up right where it is. Mainly, it is these are the same. The same strategies that apply to any general instrument also applies to our experiment.
Right. And maybe we can have one last question. Other than studying universe and galaxies, what are the other uses that radio astronomy is used on Earth's surface? Let's say if I conduct radio astronomy on the surface of the Earth, apart from studying the universe in general, is there any other application that I can go for?
So I answer that in two different perspectives. One is again from the astrophysics side of things because I am an astronomer. I just mentioned a couple of phenomena, but there are many, many. For example, pulsars are something that I mentioned. There are also phenomena that are we generally called transients, which come and go. It's a very, very bright burst of radio emission in the sky. And this is again an open problem in all of astronomy. These have been detected only mostly in radio, very few detections at other frequencies. Exactly causes them. It's a very, very violent and energetic release of energy. Okay. The reason why this connects to bigger picture, especially of interest to physicists, is that these are processes that cannot be replicated in any physics lab. You cannot build an particle accelerator that large anywhere on Earth to generate this type of energetic events. Okay, so these are things that we can study only in astronomy and physics better, fundamental physics, particles, acceleration processes, radiative mechanisms, potentially even quantum interactions. So all of this is an answer from an astrophysicist to a physicist. Okay. That being said, let's talk about more general applications to humanity and society. Okay. In general, astronomy and including radio astronomy typically tries to detect very, very faint signals also, very sensitive detections. So for this, we generally push technology to the boundary. Okay. So we make cutting edge technological inventions that are applied for radio astronomy, but then very readily translate to general purpose technological developments. One example, very, very relevant to radio astronomy, is this process of interferometry that I mentioned, that uses data from different parts to put together a bigger picture. The kind of data radio astronomy very readily translates to biomedical imaging. Okay, so the imaging in radio astronomy and imaging in biomedical for biomedical purposes, when you scan things, you do a some sonogram or ultrasound or MRIs. All of these underlying mathematical foundations have been refined in radio astronomy. Okay, so that is one example from a from a societal application of what radio astronomy can do. And the other answer I hopefully have covered, transient example, which is not the same as studying the evolution of the universe.
Right. Yeah. So I think, excuse me, we can conclude our session with this. So thank you so much, Dr. Mayuri, for walking through this incredible journey. Thanks again.
Yeah. Thank you. Thanks, Mohit, and thanks once again to Praveen sir and to Start. Thank you.
Thank you, Dr. Mayuri, for providing an informative talk on radio astronomy from ground as well as from space. And also our thanks to Mr. Mohit for well moderating this session. Thank you once again.
My pleasure, sir. Thank you.
Bye.
With this, the lectures in the sub-theme space-based astronomical observations is over. The next sub-theme is instrumentation and technology for space-based exploration. in which there are 7 lectures are there. Today, in this second lecture of today's, we are going to hear about optics in space by Dr. B. Vishweshwar Rao, IIRS-ISRO, Bangalore. This session will be moderated by Srimati Lakshmi. Presently, she is working in Program Planning and Evaluation Group, and she had also worked in optics systems area of LEOS as well. May I welcome Srimati Lakshmi to moderate this session. Over to Srimati Lakshmi.
Thank you so much, sir. So we'll start with our next session, which is optics in space. Your speaker, Dr. B. Vishweshwar Rao, is currently heading the Reflective Optics Systems Division of LEOS. He received his master's degree in engineering physics with a specialization in photonics from NIT Warangal and his PhD from the Department of Physics, Indian Institute of Space Science and Technology, with a focus on space-based freeform optical systems. He joined LEOS, a premier unit of ISRO, in the year 2006 and has been working on fabrication and testing of precision optics. He has contributed to various missions, including INSAT-3, Cartosat-2, Resourcesat-2, Astrosat UVIT, Cartosat-3, and the recent Aditya L1 payloads. His work also involves the development and testing of large aperture, high resolution optics, super smooth surface roughness mirror optics for future missions. His current research interests include freeform optical systems, segmented mirror telescope, and digital holography for optical testing. He has authored 20 papers in national and international journals. He is the recipient of ISRO Young Scientist Award 2015 and ISRO Team Achievement Award for Astrosat UVIT optics in 2015 and for the Cartosat 3 optics development in 2018. Over to you, sir, for the session.
Yeah, thank you, Lakshmi, for the nice introduction. Am I audible to the? Yeah,
Yes, you are audible.
I'll share the presentation. Yeah, good evening to all. Yeah, today I am going to give a lecture on a topic which is assigned to me, optics in space. Yeah, this picture depicts here how space-based optics is being used for the imaging purposes of astronomy and remote sensing of Earth and other applications. Coming to my lecture, outline of this lecture is fundamentals of optics we usually deal with, an electromagnetic spectrum where we are working now, and space optics, what are the types of space optics we have and applications of space optics, what are the challenges we are going to deal with, and key requirements of space optics and optical instruments in space and future trends in the space optics, along with some conclusions. Yeah. So basically, the term optics is a branch of physics that deals with the study of behavior, properties, and application of light, where you can see these are the properties like reflection, absorption, refraction, where you can see the light is reflected here back when you deal with the rays nature of the light, and absorption and refraction when it passes through one medium to the other medium, and the same optical properties of which gives a scatter when it falls onto a rough surface, it scatters the light. And a next parameter property, which is like a diffraction, when it passes through obstacles and how it diffracts. And also it includes interference, where the interference of two waves will form and give a surface properties of light and where it is fallen and other things, and polarization effects, And being a light is a dual nature, which is the intensity it has got, and also waveform. Energy and waveforms are also dealt with. So space optics plays a fundamental role in observing the celestial bodies, understanding cosmic phenomena, and enabling space exploration technologies. Most of the information about the universe, it reaches through electromagnetic spectrum. So we know that space is having a very high vacuum, and electromagnetic radiation can travel vast distances without significant scattering, making it an ideal astronomical observations. Light in the form of electromagnetic radiation travels through space at a constant speed of 3 into 10 to the power of 8 meter per second, as you are everybody aware of it, because sunlight reaches the earth in 8 minutes 15 seconds. That is the calculated value. So the term space optics refers to the study and application of space optical systems in space environment. So in space optics, scientists study a different wavelengths of electromagnetic radiation, including visible light. Adjacent to here on right side, I have shown that what is the frequency and wavelength spectrum we are dealing with. Generally, gamma rays, X-rays, ultraviolet, visible, near IR, infrared, and thermal IR and far IR. Most of the times, it will be optical imaging will be done in this region where ultraviolet to far IR region. In the previous lecture, we have heard about the radio waves and microwaves and long wave imaging using antennas. So each wavelength provides a different information about the celestial objects. Like if you take infrared radiation, helps to detect the dust clouds and star formation, and X-ray reveals high energy phenomena such as black holes in the space, and radio waves will study the cosmic microwave background radiation. Coming to optical instruments which are useful for astronomers and astrophysics, they are telescopes, imaging sensors, and followed by spectrometers and optical communication systems, optical navigation systems used in satellites, space probes, and space telescopes. Why we want a bigger optics, means large aperture optics? It is because of this resolution. We need a high spatial resolution, and we need to gather the more light energy. Coming to this equation where resolving power is given by 1.22 lambda by d, where in this particular equation, d is the diameter of optics and the lambda is the wavelength of light which we are using for imaging. So as the diameter increases, you will get a very high resolution imaging. And generally, this optics is have a limitations which in terms of aberrations and diffraction limit. So we call it as a diffraction limited optical systems, because these are bound to happen because of the diffraction phenomena. Coming to the telescopes, what type of telescopes we may have? The mostly reflective and refractive. So most space telescopes use reflective optical systems rather than refractive lens assemblies, but very few, because it depends upon the application which you are looking at. If you see reflective telescopes, they use mirrors, which is a property like reflecting properties of mirrors are used to collect the light and focus it to the sensors. And advantages what we have here, there is no material property involved, so no chromatic aberration is there. Because of this advantage, we can have a large aperture possible. And because when we are talking about the space telescopes, we need to have a very lightweight optical systems. To have a lightweight optical systems, we need to make even the mirror to be lightweighted to a very less mass and compared to other structures and other things. So in primary mirror, most of the times it will be you can see a depiction shown here. If there is this is the particular configuration of light telescope where you have a bigger primary mirror. Let us say it is 1.2 meter to almost 2 meter size, and we need to have a thick. When you go for a thicker blanks, So weight of the telescope and weight of the spacecraft carrying it will be have expenses which will be charged by launching agencies. So what general procedure is followed is, this particular mirrors will be lightweighted. I'll show in a present coming slides how it is lightweighted. Lightweighting of the mirrors will be done from the rear surface of the mirrors, and almost 60 to 70, even now people are going to up to 80% lightweight of the mirrors. And these mirrors, when let us say in this configuration, when the radiation, earth radiation, if it is looking at the earth or the sky, the radiation falls on the primary mirror and it will be focused by diversion. In this configuration, this is a primary and secondary mirror, and it will be focused to make a compact system to the sensor detector. So this is the phenomena generally for large telescopes, they configuration they follow. Then coming to refractive, if there is a wide field of view requirements are there, then mirrors generally don't have the wide field of view imaging. When it comes to the lens, it can take up to 40 plus or minus 45 degrees field of view. So refractive telescopes uses a lens which will use the bending, refraction phenomena to focus to collect the light and focus it to the detector. Rarely, because they have some disadvantages like chromatic aberrations, because every wavelength will not be focused to one particular focal point in the image plane when it comes to the refractive, because of transmission properties will be different for different wavelengths, and because of which you cannot have a larger telescope lenses. Homogeneity of the lens material is more important here. If you see on the right side, there is a lens assembly with the mount and the lenses, series of lenses. They are optimized to have less chromatic aberrations when the different wavelength of light passes through them and gets focused at the detector plane. So lenses are limited up to, we can say up to 500. People have done 500 diameter lens, beyond which there is the availability of material with good homogeneity and refractive index uniformity. It is very difficult to make. So that's the reason people generally prefer, based upon the applications only, refractive systems will be used in the space optics. You can see adjacent to on the right side, there is a lens assembly which is for imaging the space, and here this is the earth imaging satellite, where it configuration wise it is shown in the picture. And there are the manufacturing limitations also in the refractive system because of the availability of the glass material. Now coming to the space optics applications, first applications which our ISRO we are doing is the satellites equipped with the Earth observation or climate change monitoring, forest cover, ocean currents, such as natural disasters, and even cartographic applications where we can image the Earth surface, and it will be used for our planning and strategic applications, also town planning and strategic applications. Other application of space optics is observing galaxies, stars, planetary systems, which help the scientists to understand the origin and evolution of the universe. So planetary explorations, further it can be taken beyond the galaxies at advanced optical techniques like transit photometry or coronagraphy. Recently, we had a launch of Aditya L1, which was aimed at for coronagraphy to detect the our star, like sun, detecting sun coronagraphical imaging, which helps the other. What is the features of the sun coronagraphy? It was detected in the Aditya L1. Yeah, coming to the challenges in the space optics, like because we know it is in extreme conditions such as vacuum, extreme temperatures, radiation of the means other wavelength radiation, it can damage the telescope. There will be a microgravity effects when it is going to the deep space, and the contaminations. And designing optical systems, we have to take care of all these challenges and design a optical system which can withstand, and the spacecraft experience extreme temperature fluctuations, like it can go from minus 150 degrees to 1 plus 120 degree. and alignment of the components within the mechanical structure need to be maintained with this temperature excursions. And when there is a high radiation, cosmic radiation, it can also cause the damages to the electronic components and optical sensors. These are the challenges involved. And optical systems can function accurately without gravitational support structures. But problem is we need to have a support structure to hold the optical systems. So microgravity, how it is going to impact the distortions of the support structure also we need to study. Then contaminations when it comes to outgassing, micrometeors, which can degrade optical surface and reduce the system performance. So engineers need to take care of all these parameters like material, coating, and protective shields to overcome these challenges. So next is the requirements. When it comes to challenges, what are the requirements we need to take care? Like space telescope mirrors, generally we need to have a low thermal expansion, which prevents the distortion due to temperature variations, and high stiffness to weight ratio. When we are going for the lightweight, because bigger mirrors we need to do a lightweighting operation, but it should have a high lightweight percentage and also high stiffness. And generally good polishability. All the materials we cannot make use of making a mirrors to achieve nanometer level smoothness. So we need to have a good polishability of the particular glasses which we are using, and thermal stability to maintain the cryogenic temperatures. Even at the lower temperatures, the optical surfaces should not degrade. And the same thing which has to survey the radiation resistance. So what parameters we will take is weight. Weight versus stiffness, and thermal stability versus manufacturability, and cost versus performance. These are the how we will trade off between the materials. The common materials what we use is beryllium, which dominates in cryogenic temperatures and IR telescopes. Glass ceramics like zero door ULA, which are used for the visible astronomy. Now, recent technologies have silicon carbide, with all silicon carbide mount and optical surfaces as emerging as a stronger competitors in this case. So each optical surface, we need to have a better image quality. To have a better image quality, we need to have a surfaces which are lambda by 50 RMS surface figure, and other if it is a spherical or aspherical surfaces, what is the accuracies we can maintain, sagitta variations along the surface we need to maintain, and how the optical surface roughness, it should be within less than 10 Armstrongs, and overall optical efficiency of the system should be greater than 92%, and integrity or functional integrity of mechanical and structure, and when it going through the thermal loads, so optomechanical integrity should be better than 1 micron. These are the critical requirements which demands for the space-based optical telescopes. Yeah, when it comes to when it comes to what is lambda by 50 RMS, what we are telling, in this picture we can see there is a long 700 mm diameter mirror. From the pattern you can see it is some flower pattern is seen, but the front surface what we have is a mirror surface. From the ray surface we have done the lightweighting is being done, and the maintaining the stiffness parameters. And if this particular surface is having a 700 mm diameter, it is equivalent for this space telescope. It is equivalent to the surface undulations. Lambda by 50 is nothing but equivalent to surface undulations of bigger like Bangalore Cricket Stadium. If you see that undulation should be 1 micron level. So entire area in the stadium, it should be to 1 micron level. To that accuracy, this optical surface need to be there. So that is the lambda by 50 RMS requirement for imaging of the optical telescopes. So optical instruments which you have used generally, so space telescopes in orbit, they'll be placed in orbit around there, and you are in the deep space to observe the objects without interference from atmospheric surface. So atmospheric surface absorbs and distorts the wavelength during the images. Nevertheless, ground-based telescopes are also available. I'll come to the next slide where there how ground-based telescopes can also be used for astronomical observations there. And in fact, they are the one which started, people started in a long time back. Then only it ventured into the space-based telescopes. So we can overcome this atmospheric turbulence effects using space-based telescopes. We can have a very good high-resolution images and continuous observation capability, and which we can access the full spectromagnetic electromagnetic spectrum. Like when it comes to imaging UV to far IR, we can take the better examples. What we have, Hubble space-based telescope and James Webb telescopes, which we can see the first image of James Webb telescope, which has shown about the galaxies and other stars clearly seen. This is the Hubble space-based telescope, which was launched almost 30-40 years back. Yeah, next application which we use is a spectroscopy in space. So using a spectroscopy, one of the powerful optical techniques, we can analyze the space. We can use it in space science, which analyzes the spectrum of light emitted or absorbed by the particles. Like if you have a continuous source, when it passes through the cloud of glasses, it have an emission spectrum and absorption spectrum. So using these emission spectrums and absorption spectrum, we can determine the chemical composition of stars, temperatures of celestial bodies, and velocity of galaxies. I'll come to next that how redshift it happens, and atmospheric composition of planets. Even like recently we have seen that Mars rover and our Chandrayaan-3 also had optical instruments which have detected the manganese and other chemical compositions of the lunar surface. So based on using these instruments, we can detect what are the spectral features of the surface of the lunar or so other exoplanet atmospheres we can see. Yeah, studying the light spectrum identifies the stars. So when we have come across that cosmological redshift, whatever the wave which is emitted by the star, it reaches over a time. As per time passes, wavelength expands, and slowly it will be detected by our telescopes which are in the space. So there is a shift in the wavelength, which clearly shows that whatever the detection we are doing from telescope, it has been traveling a long distance, and young stars what we have, that only we are detecting and analyzing using cosmological redshift. If the objects elements are unique spectral signature, means their objects are moving away from the observation, and if they are blue shift, which then the objects are coming very close to the telescopes. With this, we can find out what is the velocities and what of the each stars are celestial bodies. And other optical systems which are very much required, general spacecraft use sophisticated imaging systems for scientific research. They are CCDs, and where for Earth observations we generally use CCDs and CMOS. So CCDs will have a very small pixel sizes, like up to 7 microns, 8 microns. These are the sensors. Charge coupled devices which convert the incoming photons into light and into electronic signals, and these signals are extremely sensitive and can detect the faint celestial objects. And firstly they were used for our Earth observations, and we can get the high resolution images. Then they have been used for the celestial object detection. So advantages of the CCDs are having a high quantum efficiency. So whatever the light it is received from the telescope, it will be connected into electronic signal, and we can get the very good images with low noise and high spatial resolution. So widely astronomical telescopes and satellites, they make use of the CCDs as a sensors. And very recently, the more modern spacecrafts are using CMOS based, which is the which consumes less power, I can show, and provide a faster data processing with the improved chip design and other features are included in the CMAS. Other application which are optics in space is optical communication, where it is we can use optical beams for as a medium for communications, communicating the data. Generally, instead of radio waves to transmit the data from satellite to Earth or to satellite, we can make use of a laser beam, which can transfer high energy laser beam, which can be transmitted from the ground to satellite. And because of the narrow beam transmission through of the laser, when it reaches to the spacecraft, a receiver will be taken, and from that data can be transmitted to other satellites or another point in the Earth surface. So this optical communication is a faster and reduced interferences will be there, and the higher data rates can be obtained using this optical communication. NASA is already, and other space agencies are currently using optical laser-based communication systems for deep space missions. Even ground-based optical communications are also in place now. Presently, one terminal to other terminal, people have exchanged the data transmission with the higher data rates. Other optical systems which are there for, that is to navigate and guide the optical telescopes or spacecraft which are already there in the space, like star trackers. So generally these star trackers, you can see here star tracker photograph, where it will collect the very faint star lights, and it will register into in the this one catalog. So there are the different magnitude stars are available, and they have been catalogued over a time since 40, 50 years. So we know the orientation and position of the spacecraft with respect to different stars in the space. And with that, we can know the attitude of the spacecraft. There are different sensors like sun sensor, earth sensor can also be used, but star trackers have got the better accuracies, pointing accuracies within 5 arc seconds. Um, Recently, even 1 arc second star trackers are also developed by LEOs, ISRO, and they are being used for the spacecraft stability requirements for cartographic applications. When it comes to a nevertheless, there is a optics in space that still we can image using ground-based telescopes, but there is a problem of atmospheric turbulence, which plays a greater role in the ground-based telescopes. They have been corrected using adaptive optics, wherein the light signal which comes from the star light, it is turbulated by atmospheric turbulence, and when it reaches to the sensor, there will be a feedback loop to the wavefront sensor, which takes the reference star, and it will continuously correcting on the using a deformable mirror. There will be a deformable mirror which corrects the position sensor, and it will annul the turbulence which are already formed, and it images the stars. You can see there is a difference with adaptive and without adaptive, how the stars are being imaged. There is a correction of the wavefront corrector using deformable mirror. So there are techniques which can be done, and the same technique, some of the techniques are being used in space-based telescopes also, where deformable based on the ground calibrations of the Earth observations, they are used deformable mirrors and corrected the image quality of the telescope. Still further, image analysis, image processing also been used for the processing of this data, apart from the adaptive optics. So systems continuously will adjust this distortions of incoming light, and we'll get the clearer images. So future developments in space optics is we are going ahead. We need to have a high resolution images of space and Earth observations. We need to have a bigger diameter optics mirrors. So next generation telescope will use large segmented mirrors that can be folded and unfolded in the space to achieve extreme high resolution. So we have a good example of James Webb Telescope, wherein 6-meter telescope aperture is folded in this fashion and stowed into the spacecraft, and it is deployed in the space during the deployment operation, and we got a very good images from the James Webb telescope. And another technique, which is space interferometers, we can combine a multiple telescopes to simulate and much larger telescope apertures, which they are in an array of telescopes can be placed in one order in a fashion. Then we can club all those images from the multiple telescope to simulate a much larger telescopes. So recent applications like quantum optics in space. So using a quantum mechanics phenomena, this quantum optical systems can be used for ultra secure communication. Like I spoke about the optical communications, using quantum optics, we can communicate the data with high accuracy and high precision and secure way of sending the data from spacecraft to another spacecraft and spacecraft to down. So upload download links can be made using quantum optics in the space. And another technique where we can use many miniaturized CubeSat optical instruments for small satellites, and making because affordability and space research also we can improve using a smaller miniaturized instruments which can aim at a particular wavelength and a particular application, and get the more benefits out of the smaller miniaturized optical instruments. So coming to the conclusion, optics is very much essential for this Earth and space sciences, which enables observation and communication navigation. So advancement in our space optics has revolutionized our understanding of universe, and which can observe distant galaxies, analyze the planetary atmospheres, detect exoplanets, study cosmic wave backgrounds, and unlocking mysteries of universe. Thank you, and I'm open for question and session.
Thank you, sir. Thank you for that insightful session. Now we will have the question answer session. If you can stop sharing the screen, we can see the questions. Go back to the Chrome. New message.
Hello.
So the first question will be, how do extreme conditions in space, like temperature variations or radiation, affect the performance of optical systems at a fundamental level?
Yeah. Generally, this I've already dealt in my presentation that this radiation and temperature excursions will deform the optical surfaces, because the requirements are like lambda by 50 over each surface. So when these radiation and temperature variations are even if you take care of design aspects and other things, unknown changes at particular wavelength and localized heat content in the optical surface in the path of the telescope, that can degrade the optical performance, like imaging and other aberrations will be included in the system. So imaging will be aberrated image, because of which we need to take care about the temperature excursions and radiation effects.
The next question will be the effect of cosmic radiation. Is it similar like the atmospheric effect in telescope data?
Yes, that is a good question. Cosmic radiation, which have a different like gamma rays, X-rays, but still it may not impact immediately. Over a time, it will degrade the coating of the mirrors or optics which is there, and on the surface roughness will increase, because of which we will have scattering of light and the signal losses will be there. So we need to have a protection mechanism. Generally, whenever there is an imaging, there will be imaging slots fixed in during the using space-based telescopes. So imaging slots will be taken up. Other time it will be covered and it will be protected. So that is the reason to have a bigger lifetime of the telescope. General tendency to have a protection mechanism and avoiding the direct radiation falling onto the optical systems. They use different baffles and hoods which can cut down the incoming radiation coming from inside, and it will be absorbed by black absorbent coatings also on the vanes of this baffles. So some protection mechanism is already will be taken during the designing and engineering aspects, but still there will be a lifetime limitation of this optical telescope. Generally, we target for 7 years. It can go up to 15 years with some extra protection taken care during the realization of the spacecraft with the hoods and the baffles and other protection mechanisms.
Another question, sir, it is about the resolution. So how do space-based space telescopes like James Webb overcome the optical aberrations and diffraction limits to achieve high resolution imaging in deep space?
Yeah, it's a good question. Like how to overcome the optical aberrations? Actually, optical aberrations at the design stage itself, they are being optimized at each surface. How telescope is not only a single element, a mirror which it has a including primary, secondary, tertiary. There will be a four elements which will be designed at a design stage to have a diffraction limits. Nevertheless, when it will be deployed using like James Webb, it is deployed in the space, and alignment is more critical there. So alignment related optical aberrations are bound to come, but that was done using a starlight calibrations. Each mirror, like when it comes to if I go to this particular website, sorry, I'll just share. I need to share it. Yeah. So alignment is more critical, and the alignment causes aberrations. So aberrations can be corrected using proper actuators used in the James Webb telescope, where each segment is aligned with respect to each other and get the focused spot. So that is the alignment criticalities are involved in the segmented mirror telescopes. But nevertheless, it is done by James Webb using different types of actuators which have the freedom of alignment in all degrees of freedom. So it is been aligned, and using a star trackers, they have been aligned. So with that, we can get a very high resolution, and high resolution generally depends upon the wavelength of imaging and also the diameter. Here in James Webb, it is 6-meter diameter telescope, which can achieve better resolutions compared to previous Hubble telescope, which is only 2.4 meter diameter. So and it is operated. James Webb is operated at IR wavelengths, so accuracies are little less compared to visible region, but it has shown a very good pictures, high resolution pictures using James Webb with the 6-meter diameter aperture.
Okay, sir. We have one more question. If we could build a telescope on the dark side of the moon, would the optical quality be significantly better than a telescope floating in free space? I suppose the question is about canceling the noise from the sun, the light from the sun, probably.
Yeah, actually, we require actually very low. In generally, the darker side will be imaged by IR imaging telescopes. There also we need to have a very good radiation and temperature. These are darker sides will be very cool. So we need to maintain the telescope operating in that cool temperatures. Materials of the telescope we need to take care during the design aspects itself. There is a possibility that darker side of the moon also can have a better optical quality, but compared to only now darker side of moon, people have not yet ventured for imaging. Even for the orbiters, what we have, orbiters have taken our Chandrayaan-2 has got a OHRC orbiter which has done the mapping of the moon or global part of the moon, and it has taken different images in IR region. There the criticality is maintaining the temperatures of the telescope, because when it goes to the darker side, it will be a very cool, and we need to maintain the heaters. So the electronics when it is cooled to a lower temperatures, their functionality aspects will come into picture. So for Chandrayaan-3, Chandrayaan-2 OHRC telescope, which we have made, ISRO has made, it has mapped the darker side of the moon also. So 3D map of the optical lunar surface is being done using orbiter. So it is possible, but you need to make it take these considerations during the design, fabrication, integration, and at every aspect, that it has to be maintained, temperature has to be maintained within plus or minus some 5 degree from the ambient. So when it is maintained at that temperatures, even dark side of the moon also can be done. The imaging can be done.
Okay, sir. I think with this we can conclude this session. Over to you, Praveen, sir.
Thank you, Dr. Vishweshwar Rao, sir, for
Yeah.
providing an informative and an interesting lecture on optics in space. And also our sincere thanks to Ms. Lakshmi for well moderating this session. Thank you once again. So for all the participants, we will meet tomorrow the same time. Thank you.